Hello everyone, welcome to this video. In this video we are going to see the properties of dihedral group. So here if you remember, this was the Keller table for the dihedral group D4, right? Now you know exactly how do we create this table, right? And here the group the elements which were taken were R0, R90, R180, R270, the horizontal reflection, the vertical reflection, the diagonal reflection, main diagonal reflection, and the other diagonal reflection. These were the elements, and we were composing these in order to obtain the other motions of different of the symmetries of a square, right? Now we'll use this thing to understand what all properties this dihedral group shows. Now already I am calling this to be a group because I know it is a group. For you, you will be knowing that D4 is a group by knowing what all properties are required in order for a set together with an operation to be a group, and in addition this dihedral group have what all properties. So this is what we'll be talking about in this video. So let's move ahead and let's try to understand the properties of this group one by one. So here we have the first property, whose name is the closure property. Now what does this property does? If you remember, when we were talking about a binary operation which was represented usually by star, it took two elements A and B, and it give you C as another element if these two elements were present as some element from S, then this C is also an element of S. So this is what then you call this to be the binary operation, where you input two elements and you get one single element as the output. And here this give you this element which is present in the same set, right? So knowing this fact, this is what is the closure property. So this closure property would also we'll check this property also for group. Why? Because the operation that we are taking in checking a group is actually a binary operation. We'll see the details in the formal video about groups. So here this property is a requirement for any mathematical system to be a group. This is one thing. Another thing, mathematically, if you call one element out of these 8 elements which we were talking about in D4, if we take the name the first element as A, and if we name the second element as B, then if we compose both A and B, then because they are in D4, then their composition AB should also be there in D4. If that is so, we say the closure property holds for A and B. And if we check it for all the elements, then we say D4 has the closure property for all the elements, right? So the question that they are asking here is does this property, closure property, hold for each composition of elements of these elements which are present in this set? The answer is yes. How? You can check it for every element. Now how is this so? If you take one composition as R270, so R270 is here, right? And you take another one to be H, right? H is here. So that means we are talking about this particular element. So their composition here is D, and D is again one of the elements of this set, right? If that is so, that means this composition holds the closure property. And again we have to check it for all the compositions. So you see, this could be very easily done through this table. How? You know, you have listed all the elements, the first elements here as these rows, right? And the second element as the columns here, right? So using this fact, and you have result, whatever is the resultant of composing, say, this element with this element, that is this element, again doing the composition of this element here with this element, that is this element, and so on. So you see the resultant is written here by the blue color, and all of the blue colors, they have only the elements as R0, R90, R180, R270, or it could be H, it could be V, it could be D, or it could be D dash, and no other element beside this. So that means the closure property hold here in case of D4 for every element, right? When you compose any two of these 8 elements, you will get back an element which is also among these one of these 8, right? So this closure property holds here. The next property is existence of identity. Now what is this property? Existence of identity. Now you should note that the identity is required for every group. So that means if you want your mathematical structure to be a group, so there should be an identity which should produce no change at all when you compose it with any other element of the set, right? So basically what we are saying if you take any element which we are naming by A, if you take any element A from the group from D4, what is D4? D4 is the set consisting of those 8 elements, right? So from this D4 we are taking one element, we are calling that to be A. A is the just a name of that element, right? Then if you compose that particular element with R0, you will get it back as the same element, or you compose R0 with that particular element, you will get back the same particular element. So in this case I have told you R0 is the identity, but if I ask you what is the identity of any random group, then how would you check? The first thing that you will do is you will see that composing with which element here give me my answer as the same, right? So we have to check this. So you see here you have R0, here you have R0, here you have R90, R90, R180, R180, R270, 270, H, V, D, and D dash. So that means whole of the elements here, all the elements here are the same as these elements. So that means when you compose with R0, when you perform R0 with any of these 8, you are getting back the same element, right? This is one way to check. Another way is you could check it like this. So here you see we have R0, R90. Why this is so? Because R0 is here, right? R180, R270, H, V, D, and D dash. So that means whenever you are doing R0 with R0, you are getting R0. Whenever you are doing R90 with R0, you are again getting R90, right? The same element back. When you are doing R180 with R0, you are getting R180. When you are doing this H with R0, you are getting back H. So you see this R0 is creating no effect on all the elements. So we have observed this in both directions. So therefore we can conclude that R0 is the identity for D4, the group D4, right? Because it produced no change at all whenever you compose any other element of D4 with R0. So here R0 is the identity, correct? So this is the second property that I was talking about. If you take A as any element of D4, then if you compose that with R0, because R0 is the identity in this case, so we are getting back the same element, right? So that is same as saying that if you combine any element A on either side of R0, you are getting back the same element. The next property that is essential requirement for a group is that for every element we should have an inverse element. Now what is this inverse element? So to understand and calculate what is the inverse, we should know the identity. So for D4 we know what is the identity, it is R0, right? So basically we are looking for an element. Suppose A element is given to you, so we are looking for some element here such that when you compose this element with A, you will get back an element which is nothing but the identity of the group, and in this case it is R0, right? So here we say this thing for each element which is present in D4, we are calling that to be by the name A, right? there is exactly one element B in D4, so that element should also be in the same set or in the same group, and such that we have the condition that when you compose the first element with this second element, you are getting back the identity, or you are composing the second element with the first element, you are again getting back the identity, right? So in this case, if this happens, so B is said to be inverse of A and A is said to be inverse of B, right? So they are both the inverses of each other. And so here you notice that, what does that mean? It means that on a square, when you apply the operation A, and after that you first of all you apply the operation B, and then you apply the operation A, then you are getting back R0. So that means whatever action you have performed by both of these is represented by R0. So for the symmetries of a square, R0 means rotation by 0 degree. So that means you are not doing anything at all, because we are not rotating anything at all. So whatever is done by B is cancelled out by A. What does that mean? It means that if you rotate by 90 degree the square twice, right? So this is the action, say supposed performed by B. So A will do what? It will rotate the square 90 degree twice, but in the clockwise direction, right? So this is what the operation B does. So actually what you have done by performing these two actions simultaneously, one after the another, you have again reached at the same initial situation in which you were present before performing any of these operations, right? So here the effect of one is cancelled by the effect of another, and that is what I have listed here in this note. So here you can clearly see that if A and B both are inverses of each other, then B will undo whatever A does, and A will undo whatever B does. And as I have told you, this R0 is rotation by 0 degree. It represents no change because it in this case acts as an identity. Thus, therefore, the effect of both A and B, when they are taken together, that produce no change at all. You can see this through an example. I am saying this R90 and R270, they are inverses of each other. So that means by definition, R90 when composed with R270 should give you R0. Is it so? Let's go and check back at our table. R90 is here. When you compose this with R270, you will get back this element. And what is this? This is the element. This is the identity element R0. And similarly, if you take R270 first and R90 second, so then in that case also you are getting back R0. So you, in this case, both R90 and R270 are inverses of each other. So to find inverse, say, suppose I say what is the inverse of D. So in that case you will see D here, and in this particular row, in the row of D, you will point out where is my identity. Here is D, V, D dash, H, R270, R90. This is the identity R0, and this corresponds to what element? It corresponds to D only. So you see, D is the inverse of D. So basically D will cancel out its inverse. So you see, this is the case. And if I ask you what is the inverse of this H, so let's calculate that also. The inverse of H, for that you have to locate where is my H. So this is your H, right? So in this row you will identify where is my identity. You see, here is your identity. So here this R0 is corresponds to H again. So that means H is the inverse of H only. Similarly, if I ask you what is the inverse of 180, right? What is the inverse of 180? So here is 180. So this is here, this is here, this is here. So this identity corresponds to R180 here. So basically R180 is the inverse of R180 only, right? So you see how this thing works here. You can calculate the inverse of each element, each of these 8 elements, by looking at this table. So you see, this table make your work so easy in order to perform all the calculations, right? So this is about inverse, and V is the inverse of D, right? V is the inverse of D. So you see, this is about the 3 properties. In the next video, we'll be continuing with the other properties of this D4. Well, that is it for this video. Thank you for watching.